Hi guys, Dr. Gillard here. It's week 6. It's Monday. It's spring of 2021. Let's talk about glucocorticoids in preparation for Cushing's disease. Cushing's disease, of course, is an oversecretion of glucocorticoids. So we'll kind of start dancing around Cushing's a little bit here. Glucocorticoids, what is the function of these? And we're really talking about who? Cortisol is the main glucocorticoid that comes out of the zona fasciculata of the adrenal gland. That's really who we're talking about. What's its job? Its job is to maintain blood glucose levels. So you want glucose levels. Some cells, like brain cells, they need glucose all the time. So that's one of the jobs of cortisol, is to make sure that we always have adequate levels of blood glucose. And we'll see where it comes from. Of course, you probably know already from biochemistry. It comes from the breakdown of muscle and fat via a process called gluconeogenesis. It's also important in stress management, which we have talked about before. We know that stress soaks glucose out of your blood like crazy. And then how are you going to replace that? Well, by secreting more levels of cortisol. So stress management and maintaining blood glucose levels. What else does it do? It also inhibits swelling and inflammation. It's important so your inflammatory reactions don't get out of control. It snuffs those out. And we'll look at how it inhibits phospholipase A2 here in a little bit. How does it do that? Or how does it cause hypertension? Because that's another thing it can do. Right? It's not maybe a main function, but over in Cushing's disease it is. If you have too much cortisol, you get hypertension. How does that work? There's two, and this is still not completely understood, but it's thought, and I think I've mentioned this before, it sensitizes norepinephrine receptors. And remember the balance between nitric oxide and sympathetically released norepinephrine, which is released. Where is it released? Tunica. No, not in tunica media. Tunica adventitia. It diffuses, the norepinephrine diffuses in, binds to its receptors in the tunica media, and causes vasoconstriction of the smooth muscle, which crunches down on the lumen. And it's thought, some research says it sensitizes these norepinephrine receptors, and therefore it responds to norepinephrine too aggressively. And if you over vasoconstrict, that's hypertension. It also stimulates the sympathetic nerves that go into the tunica adventitia to over-release norepinephrine. That's another proposed mechanism for ADA 2015. In addition, the binding to MR receptors on principal cells. So glucocorticoids can bind to principal cells in the kidney and act like aldosterone in really, really high levels. And so that's another effect, where if you act like aldosterone, you're reabsorbing salt in water. You're kicking out hydrogen ion and potassium into the filtrate, into the urine, basically. Remember this thing. We'll look at this again. I'm not going to go through this again. This will be on your midterm, though. But look at the very top level. Get a tissue injury. The cells get damaged. They release, amongst other things, they release an enzyme called phospholipase A2. And that starts the cleanup process, right? Inflammation is a cleanup process. And it's a fighting process. We want to kill bugs. We want to clean up damaged tissue. You run this inflammation process. And the very first step, steroids, corticosteroids, and not just exogenous corticosteroids, but any type of cortisol, it binds to phospholipase A2 and shuts it down, so it can't fire up the inflammatory cascade here. Basics of glucocorticoids. The main glucocorticoid is cortisol. Corticosterone is another one released. Where are they released from? I know the adrenal cortex, but more specific. Zona fasciculata? Yeah, zona fasciculata. Remember GFR, granulosa fasciculata reticularis. So their middle layer is where they're released. They're released, let's see, we just said zona fasciculata, normally stimulated by the binding of ACTH. I haven't said this yet, but sympathetic nerves also plug in to the zona fasciculata, and an overproduction or an over outflow of sympathetic flow out of the tiger cage, out of the vasomotor center, usually driven by stress, can fire cortisol, can stimulate the release of cortisol as well. We talked about how overproduction of ACTH does that via the HP axis. So glucocorticoids are considered a member of the HPA axis, the hypothalamic pituitary adrenal axis. Okay. Are glucocorticoids cortisol a member of the HP axis? No, it's not released from the hypothalamus or the pituitary. It's a member of the HPA axis. The main one's cortisol is the main glucocorticoid. We said 95% of all glucocorticoid activity comes from this. And again, it does have a significant mineralocorticoid effect. It can bind to MR and does bind to MR receptors. Aldosterone's receptors are MRI receptors. Not great affinity for these, but the plasma concentrations of cortisol, 2,000 times greater than that of aldosterone, so it does have some widespread effects. Some fun facts: 90% of cortisol actually is carried on corticosteroid binding globulin. Only 10% actually floats free in the bloodstream. Free cortisol is more biologically active than bound cortisol. More fun facts. This is a very important fun fact. This is alpha-glucocorticoid. Oh no, this is not yet. We're coming to something different. But cortisol binds with high affinity to its GR receptors, which are specifically called alpha-glucocorticoid receptors, or type 2 receptors, type 2 corticosteroid receptors. Their target is not on the cell membrane, it's inside the cytosol. Remember, cortisol is a steroid, so it can just pass right through the cell membrane like nothing, like a ghost. The cell membrane is very hydrophobic, just like cortisol. I'm sorry if you hear that noise. I don't know what's going on outside, but sounds like they're tearing down a stop sign or something. Complex is taken into the nucleus together then, and it targets genes and does what it's going to do. Heat shock proteins, there's a whole lecture I got rid of. We're not going into the weeds on those, but they're really important. They cover the binding sites for cortisol in the cytosol, so they're very important. Cortisol does not bind to beta glucocorticoid receptors, only alpha glucocorticoid receptors. Now, cortisol in the kidney, I think we've talked about this. I'm not sure if we did or not, but this is really important. So if cortisol can bind to mineralocorticoid receptors like aldosterone's receptors, that's not good, right? Because cortisol and aldosterone can both cause the reabsorption of salt in water. Well, that would be true, but there's somebody who stops that. There is a monster, or a what can we call this? There's a enzyme that stops this, and it's super heavily produced in the kidney, and it's called 11b-hydroxysteroid dehydrogenase type 2. 11b-HSD2 is how we'll just call it for testing purposes. It's really, really important. What does it do? It grabs that cortisol. Any cortisol that wanders into the kidney and gets near the principal cells, because it can bind to those MR receptors just like aldosterone can. It grabs the cortisol and converts it into a similar molecule called cortisone. So 11-beta-HSD2 grabs cortisol by the throat, and cuts off its tail and creates a new molecule called cortisol. And cortisol cannot bind to, not very well anyway, it can't bind to MR receptors nearly as much. So very, very clinically insignificant amount of cortisol can bind to MR receptors and cause the reabsorption of salt and water. So super, super important. Who cares about 11beta-HSD2? There's a condition. And there's another condition. People who love licorice have to be careful. But there's a condition called Ames, A-M-E-S. So apparent mineral corticoid excess syndrome. Super rare autosomal recessive disorder. And these patients, the gene that makes 11beta-HSD2 is mutated. And so you have a dysfunctional 11beta-HS2 gene, and it doesn't work. So cortisol, which comes into the kidney, can't be converted into cortisol, and now you're in big trouble because cortisol can bind to principal cells via the MR receptors and act just like aldosterone. So now you got aldosterone and cortisol stimulating the reabsorption of salt and water. What's that going to do? Way high hypertension. You're going to reabsorb way too much salt and water. You're going to kick way too much hydrogen ion, potassium out into the urine. So you're going to have hypokalemia and alkalosis as well, but that's not the one that kills you. Hypokalemia will kill you. So how do Ames patients present? They present just like they have apparent, right? That's the apparent mineralocorticoid excess. Mineralocorticoid excess is hyperaldosteronism, so they appear like they have hyperaldosteronism when they don't. It's just that the gene that converts cortisol to aldosterone is broken and doesn't work. And so they're going to have very high hypertension, hypokalemia, alkalosis, low renin levels, and because R2A system's turned off with hypertension. And the aldosterone levels will be normal or even low. And that's the way you can tell, because you think, oh, they got hyperaldosteronism, but surprise, the tests come back and aldosterone levels are normal or even low. You have to repeat the tests again because you don't believe them. It's such a rare condition, but they have Ames. And this one, licorice-induced Ames. So I've always taught this, but it's come into the limelight here not too long ago. Somebody died from this. So people who eat lots and tons and huge amounts of licorice every day, real licorice, they can develop Ames. And how does that work? Well, there's a molecule in licorice, in real licorice. There's biomolecules in licorice that can be converted into something called glycerintinic acid. And you guys are way too young to remember this, because I barely watched this in the 60s myself. I can barely remember this. There's a very famous show, and there's books on this called Rin Tin Tin and Rusty. Rin Tin Tin was a German shepherd who these guys would get into trouble, and Rin Tin Tin would always save the day. But that's how I remember this. Glycerintinic acid. Glycerintinic acid. It's really glycerintinic acid, but I say glycerintinic acid. All right, so licorice, then we won't worry about what the molecules are. Licorice can be converted into rintinic acid. So what? Well, rintinic acid fits really nicely into the active site of 11b-HSD2. So it basically knocks 11beta-HSD2 out of action. So you might as well have a gene mutation for it because it doesn't work. But there's really nothing wrong with the gene that makes 11beta-HSD2. It's just this glycerintinic acid blocks it. And if it's blocked, it doesn't work, and therefore cortisol that gets into the kidney won't be converted into cortisone, and it'll wreak havoc on principal cells. And because cortisol is way more prevalent than aldosterone is, right? Was it 4,000 times more prevalent? And so the poor principal cells are just sucking up salt and water like crazy, and these patients die of cardiac arrest from hypokalemia. and notwithstanding the hypertension and the alkalosis. Right? So 9 September 26, 2020. So New York Times, a man dies after eating a bag of black licorice every day. And Mass General, which is a very respected hospital, presents this case of a guy who ate too much licorice. And yeah, the licorice was converted into glycerintinic acid. And yeah, that's the story. And what else? Remember the glucocorticoids. I could probably take this slide out, right? Cortisol is the main one. Corticosterone. Corticosterone counts for about 4% of glucocorticoid activity. It's a strange bird. You need corticosterone to make aldosterone. It's actually a step or two away from the aldosterone molecule. So it's very strange that it is also found not only in the zona glomerulosus, but it's also in the zona reticularis. See, there it is. Progesterone is converted into 11-deoxycorticosterone, which is converted into corticosterone, and there it is. So that can float out and act like a glucocorticoid, or it can be converted by, which most of it is, by aldosterone synthase into aldosterone here. So that's kind of weird. Some more glucocorticoids. Cortisone we just talked about, less potent. It's the one that is acted on in the kidney by 11b-HSD2. And now we have some synthetic. What does that mean, synthetic? Synthetic is man-made. So we have prednisone, which is 4 times stronger than cortisol. And these are all anti-inflammatories, right? We're trying to kind of use the anti-inflammatory property of the glucocorticoids by synthetically making some glucocorticoids that are a little weird looking. Prednisone 4 times as active as cortisol. Methylprednisolone 5 times as active, or 5 times as stronger than cortisol. Look at dexamethasone, 30 times as potent as cortisol. It's very long acting, very, very strong. I don't know of anything stronger, a stronger anti-inflammatory than dexamethasone. And then our hydrocortisone, we've already talked about that. That's the one used to, we can use that to treat adrenal insufficiency, right? That's the least potent of the bunch. It has a very short lifespan, so that's a good one to treat adrenal insufficiency with. Synthetic glucocorticoids were first discovered. They're first used way back in the 1940s. They're used to treat rheumatoid arthritis at first. And now they're used to treat all sorts of... Prednisone is used all the time to treat sciatica and back pain. That's well ingrained in primary healthcare providers' brains. Give them a course of prednisone and see how that does. There was a paper that really discouraged the use of it. Didn't seem like it did much good, but it does. I mean, anecdotally, it's still worth a shot. I've been on that stuff a bunch of times. Remember, always taper on that. How do glucocorticoids knock out inflation? How do they really knock out inflammation? Not just talking about that inflammatory cascade, but there's genomic and non-genomic mechanisms. You got to know these because these are from Guyton. So the genomic means it has to do with transcription, translation, central dogma. Has something to do with that. So the first thing that cortisol or any of those synthetic glucocorticoids can do, we want to stop inflammation. It turns off the genes in the inflammatory cells, like the troops, the inflammatory gang, comes in to clean up a damaged tissue or comes in to a tissue to fight an infection. So in macrophages, T lymphocytes, natural killer cells, etc., it is able to turn off the production of the pro-inflammatory cytokines. Remember, those are like gasoline. They call in even more troops. They're very important in the inflammation process. So, but remember what we said about inflammation. It goes on way too long in people. We don't know why that is. And so we need to stop it. This is a great way to stop these these inflammatory cells from calling in more inflammatory cells. So that's one thing it does. Those pro-inflammatory cytokines, of course, the ringleader is tumor necrosis factor alpha. A lot of sciatica research on that monster. Interleukin 1,2,6,8, interferon gamma. What else does it do? Well, it stops the formation of arachidonic acid by blocking phospholipase A2. So we already looked at that. So it does that. What else does it do? These genomic effects still. It turns on genes in cells that make anti-inflammatory. There are cytokines, they're not all pro-inflammatory. Some cytokines are anti-inflammatory. They're the good guys. They're there to snuff out the inflammation as well, like interleukin 10, lipocortin 1, NF-κB inhibitor. Those are good guys. And so glucocorticoids will turn on the genes in those cells that make them, like T helper cells and dendritic cells, spit those anti-inflammatory cytokines out. Cortisol versus inflammation. More mechanisms. What else? This is guiding more stuff we can do. So this is important. So it stabilizes and toughens lysosomal membrane in tissue of target inflammation. So tissue that has been invaded by a bacteria or tissue has been damaged, the cells explode, right? You destroy, inflammation destroys tissue. Infection destroys tissue. Trauma destroys tissue. And when cells explode, those little the stomach of the cell, called lysosomes, have all kinds of wicked chemicals inside that are used to kill bacteria and such. They explode and release that lysosomal juice, we can call it, and it's very damaging to healthy tissue. It's damaging to the bugs too, but we don't want that stuff. And so cortisol can toughen the lysosome membrane in the tissue that's about to be destroyed. So if the cell does get destroyed, the lysosome won't be destroyed. And yeah, it's one of the most important, Guyton says it's one of the most important anti-inflammatory functions of cortisol is making that lysosome tough, so it doesn't dump all those nasty free radicals out of its stomach. It also prevents the lysosome from, we just said that already, prevents the lysosome from blowing up and releasing its juice. What else does it do? Capillary permeability is very important in the inflammation cycle. If you want the white blood cells, like we'll use monocytes, if you want monocytes to come into the interstitium to fight a bug that's invading, you have to open up the capillary permeability so those those monocytes, for example, can get in out of the blood and into the tissue to fight. And so cortisol decreases capillary permeability. If you decrease capillary permeability, it makes the endothelial cells get tight, and it prevents it. They won't let some of these inflammatory cells in. If you decrease capillary permeability, then it's going to not let some of the troops come in, because we're trying to calm down this inflammation. The battle is over, but the inflammation is raging on, so we don't want more troops coming into the damaged tissue. So it keeps them in the blood. Okay, what else here? And then inflammation too. You increase an inflammatory process will increase capillary permeability. Tons of blood fluid will dump into the interstitium, and then you get a lot of swelling in there. We don't want that. That's got to be cleaned up as well. So by decreasing capillary permeability, you don't let the troops move in, and you don't let blood fluid get out of the blood and overload the interstitium. It also, if you have a fever going on, it knocks out fever. Interleukin 1 is responsible for that. More adverse effects of glucocorticoids. Just like COX-1 inhibitors and even COX-2 inhibitors, glucocorticoids knock out PGNE2. And we know how important that is for making the gastromucosal barrier to protect your stomach against acid. So you don't want to knock that out. Glucocorticoids will mess up your stomach. People with delicate stomachs, you're going to lose your barrier. So you better take PPIs on top of these glucocorticoids or your stomach's going to go. What else? Long-term use above physiological levels. Yes. So what if you're taking 40 milligrams of glucocorticoid of prednisone, and physiological levels about 5, between 5 and 7. What if you're taking 15, 20, 30, 40? Well, and if you stay on that for a long time, you got Cushing syndrome, right? You have glucocorticoid excess. It's like having too much cortisol. So you will start getting the moon face. You'll get the little buffalo hump. You get the pendulous abdomen. You start get wasting. You get stretch marks. And we'll talk about all those symptoms maybe tomorrow. I think we're heading for doing a little biochemistry tomorrow, I think. But yeah, you get Cushing syndrome. And then what happens when you come off? If you're on a super high level, we said, then your HP axis is shut down. It's hard to get it to start again. And some people, you never get it to start. So you go from Cushing syndrome, too much cortisol, to too little cortisol because the machinery that makes cortisone is shut off. And so, yeah, you can have secondary adrenal insufficiency, and we talked all about that already. Most glucocorticoids have both glucocorticoid and mineralocorticoid activity. Yes, this is true. So hydrocortisone, for example, has a lot of mineralocorticoid activity. That's why some people who have Addison's disease, they don't need to replace they don't use, remember we said that some people who have severe Addison's, they have to take fludrocortisone to simulate aldosterone, and then they have to take hydrocortisone to simulate cortisone. But because hydrocortisone has a lot of mineralocorticoid activity, it's kind of like taking putting cortisol in your circulatory system as well as aldosterone in your circulatory system. So yeah, you may not need to take fludrocortisone like you do in Addison's disease. This is wrong. Secondary is 27. Can I remember that? That's not because secondary adrenal insufficiency, you can make aldosterone. The exception is dexamethasone. The strongest one has zero mineralocorticoid activity. So if you're taking dexamethasone, you're going to have to take fludrocortisone as well. Okay, what about stress and glucocorticoids? Yeah, the caveman is always stressed. Saber-toothed tigers always chasing him around. Stress is no good for you, right? We've talked about that a little bit already, how you get an over-release of ACTH driven by overproduction of CRH, and ADHP really drives that system. But bottom line is you get the release of too much cortisol, and that's not good. But on the other hand, if you it's a key function to ensure body has adequate glucose levels. So if you're always stressed out, it's good that it makes some glucose it's good that it makes some cortisol, because stress will soak the sugar right out of your blood. Right? We've talked about that before. And what's going to replace that sugar? Your brain has to have sugar in your blood or you'll go down, you'll pass out. So stress will suck the sugar out, and it's got to be replaced. And who replaces it? Well, cortisol does. So high levels of cortisol will do this. Stress events, we talked about them. Major trauma, infection, surgery, illness, chronic confinement is a new paper on that. Prisoners can get this. Severe psychological stress, infection, getting COVID-19. Yeah, it sucks the glucose and glycogen up like crazy. How does it do that? Well, many mechanisms, but a big one is if you're stressed out, your heart rate's going to be going and your respiratory rate's going to be going. So your heart is going to burn up more glucose. Your lungs are going to burn up more glucose. All right. Stress also sends out more sympathetic outflow from the tiger cage, from the vasomotor center. That also drives the heart rate and respiration rate, so that burns up a lot of calories. How are you going to replace those calories? Cortisol, right? If you don't, you can go into hypoglycemic shock and die from that, right? So how do you make more glucose? That's the answer. How do you make more blood sugars, glucose? How do you make more? That's the process of gluconeogenesis. And cortisol drives the process of gluconeogenesis. Gluconeogenesis makes new blood glucose. From what? What are the precursors? What are the building blocks? Amino acids mainly, and glycerol from fat. So you break down fat and muscle and use that to build glucose. And yeah, the brain and red blood cells as well. That's another one that has to have glucose around. It can't make it has no way to make glucose. Let's see. Cortisol feeds so cortisol feeds or drives gluconeogenesis again by breaking down fat. Fat is broken down into glycerol, which is used. We can put glycerol into the Krebs cycle, and we can convert that into a molecule that is run through gluconeogenesis. And then muscle proteins can be used to run as fuel for the Krebs cycle and gluconeogenesis itself. We'll look at that next time. Stress-induced hyperglycemia and hypertension. Yep. So if you're secreting too much cortisol, well, you won't have to worry about having enough or enough sugar in your blood at least. But too much cortisol is bad as well. That can drive too much production, or it can drive gluconeogenesis too hard and result in too much blood sugar. And then we have other problems that can occur, like hyperglycemia. That's not good. That increases the risk of morbidity and death. In fact, 33% of patients in intensive care typically have hyperglycemia for stress-driven excess cortisol. And if something's not done, a lot of them become diabetic. Too much cortisol will also we know it causes hypertension. This is basically, we're talking about Cushing syndrome now. That's the problem with Cushing syndrome, hypoglycemia and hypertension. We know that cortisol has the ability to cause widespread vasoconstriction of arterioles, which causes hypertension. The exact mechanism of that's a little shaky. The hot one right now is it oversensitizes. It makes norepinephrine receptors super sensitive to norepinephrine, and it causes the over-release of epinephrine in the tunica adventitia. But bottom line, it causes vasoconstriction of the arterioles. What is gluconeogenesis? Well, it's a biochemical pathway we're going to get into the next lecture. It makes glucose from non-food precursors. So this is during a fasting state, because you can make glucose by drinking Gatorade. All right, or you can just get glucose in your system quicker like that. But what happens when you're sleeping and you're not drinking glucose? And stress is so bad it soaks up, even when you're eating, it soaks it up fast. So, but yeah, it takes and we said this already, it takes non-food precursors like amino acids from muscle. Loves alanine, hates leucine and lysine. The two L's, leucine and lysine, are not able to run through gluconeogenesis. You can't put them through the Krebs cycle either. To make oxaloacetate, that's kind of the intermediate. We'll get to that tomorrow. Glycerol from fat and lactate can also be run through. Where does gluconeogenesis? Is it happening in your muscle cells, your skin cells, your eye cells? Where is this happening? It's mainly in the liver. 90% of gluconeogenesis is going on in the liver. The kidneys can do it, and the small intestines can do it as well. Those cells, in those kidney cells and enterocytes can do it. During a fast, the kidneys can go up to, I think it's 15%. It can rise up much higher, but normally it's just a little bit. How does cortisol drive gluconeogenesis? Well, we said this already. I could take the slide out. It breaks down fat and muscle into fatty acids and glycerol. Glycerol can be used. Fatty acids cannot be directly used to make glucose through gluconeogenesis. That's a good biochemistry question. Muscle proteins are broken down into fats. And we'll look at the pattern when we talk about cortisol. A very strange pattern. The fat breakdown usually occurs in the thighs and in the arms. And you actually get fat deposition in your stomach, so you get kind of like Homer Simpson, these spindly legs. So it's very strange. What else does cortisol do? Through the central dogma in cells in the liver, it drives the production of the enzymes. Remember all those enzymes you had to learn for glycolysis in the Krebs cycle? Those are being produced, even overproduced in some cases. So cortisol makes sure there's plenty of enzymes to run the Krebs cycle and glycolysis. So that's another thing it does. It also stimulates the gluconeogenic enzymes because I just said that, didn't I? Yep. All right, that is enough. So I hope you remember gluconeogenesis and glycolysis in the Krebs cycle because we're going there. And that's, you guys actually did really good, or the students did really good on boards. Dr. Dumani is crushing it, so maybe I can take this stuff out. But we'll go through it. I think we'll go through it. We'll see. See you later.